My name is Shuo. I'm working at Bloomberg, like the AI group in London. So this work is collaborative with my colleague Edgar Ridho, and also my PhD supervisor Krisztian Balog from University of Zhang in Norway. So I finished my PhD last year and joined Bloomberg this year. So in my PhD, I'm working with table-related tasks such as like table search, table retrieval, or table completion. So for all the tasks, I'm using knowledge base like Wikipedia as the knowledge bases. So the idea is like we utilize the knowledge base in order to populate or help with the table tasks. So in this work, it's the first try we do inverse direction. We're trying to discover new knowledge from web tables in order to populate knowledge base. So because when we use knowledge base, we assume they are good. However, a knowledge base is never being complete or up to date. The knowledge base population tasks aim to complete the knowledge base. It includes two primary tasks, such as anti-linking and slot filling. So you might familiar with many like existing research. They're trying to extract new triples from unstructured text. In order to find new triples they can put into the knowledge base. So also there's a line for work trying to discover new triples from web tables, because tables is kind of very unique resource to complete and up-to-date knowledge base. So we keep the same direction. So we aim to investigate to what extent we can discover new knowledge from tables for knowledge base population. So tables everywhere. I just give you a brief idea like what tables we are working with. So there are many different types of tables on the web. We focus on one thing, which is relational tables. So in database, of course, there's relation. Here is something similar but different. A relational table have a key column such as like listing all the topic entities as well as attributes in different columns. So here in this example, like athlete, we can see a list of athletes here, like Michael Phelps and Marit Bjørgen, and and also showing their attributes such as nation, sport, years, games, and gender. This is the relational tables. For entity tables, it's very similar to an info box. It's about one single entity. So we still take Michael Phelps as example. Here is actually a screenshot from Wikipedia about his personal information. So you can imagine an entity table is displaying the different properties for a single entity. Of course, there are many different types of tables, such as numerical tables, or we call it matrix tables. And all these tables actually have very useful content. However, sometimes we might use tables only the structure. We might use tables for navigation or website, or using a skeleton of tables for like structured content in website. So in this work, again, we only focus on relational tables. So here is example to show what we have inside a relational table. American Hospital Directory, which is a table caption. So it tells what content or semantic it has in this table. And headings, hospital name, city, and staff base, and a growth pension, or this is all the headings. And also the key column, it aligns the leftmost, but it is not necessarily always in the leftmost column. It's listing all the hospitals that this table is talk about. I think now let's have a little bit closer look at the colors here. So in Wikipedia, if you work with Wikipedia tables, they have already presented the results for unlinking, because you can easily find the redirects for any mention that have corresponding Wikipedia patch. But for web tables, there are row tables. We might need to do unlinking for these entities. So here is what we did. So using an existing unlinker, we're trying to link mentions in the key column, and then we find the blue ones we called link entities. That using an unlinker, we successfully link part of the mentions in the KB. And light blue ones, like a Bocha Written Community Hospital, which are unlinked in-KB entities. So they actually have a correspondence entry in the KB, but using our linker, we fail to link them. We call it unlinked in-KB entities. And the gray part, we call it out of KB entities. So just comparing to the blue ones, right? For example, the Brandon Regional Hospital comparing to Bodies Hospital. It lies in Western, it has a proper number of beds, and also the revenue every year is actually not so bad. So you might have a question, why these great hospitals do not have a similar entry in the knowledge base? So this is actually where we get started. So yeah, so the question is, it is because maybe this hospital is not prominent enough or is not important enough at this point, or sometimes because of delays. When we create an entry in knowledge base, for example, in Wikipedia, there's like 133 days latency behind the news mention. So probably because either of the reasons. This is actually how we got motivated. And also one more interesting fact is the Google. So in Google Fusion tables, only 22% of all the entities in these tables have an entry in any of the public knowledge bases, such as Wikipedia, Freebase. So Google Fusion table used to be a table search engine and it was closed last year, but it has a bunch of new entities. Okay, then the objective of this work is to discover new knowledge in specific new entity here from web tables, web relational tables on the web for knowledge-based population. And here is the task pipeline. It's actually our solution, of course. It has two steps or components, table to KB matching and novel entity discovery. The first part, table to KB matching, it links mentions or table cells to entities and predicates in the KB by two subtasks, anti-linking and column heading property matching. So let's have a look at illustration. So for any relational table in your table corpus, what we do is we perform anti-linking. We focus on the key column. We're trying to link the mentions in the key column to find their correspondence in the KB. And also we do a schema matching. We find the headings there corresponding predicates in the KB. So after the first step, we are managed to link part of the tab cells or mentions to the KB. However, there's something left over. For example, in the key column, MT1, MT2, we call it unlinked mentions, which will be the focus of our second step. Novel entity discovery, which determines which entities need to be merged and added to the KB by novel entity classification and entity resolution. So the first task, novel entity classification, that is, given all these unlinked mentions from any relational table, what we do is we classify the unlinked mentions as in KB, after KB, and not an entity. So in KB is, yes, they are entities. They have the entry in the KB, but we fail to link them in the anti-linking step. Out of KB, we call it new entities. They are entities, but they don't have entry yet. And not entity is like minor case, where in practice, we're filtering out these not entities by rules. In the last step, entity resolution, it groups mentions that refer to the same entity together and assign an entity type. What does it mean? So because one entity might have different aliens, so what we do is we group all the aliens that are referring to the same entity together, and also we additionally provide an entity type in order to do the dissimulation. So now let's have a look of each step. The first step, anti-linking. So again, we focus on the key column or core column, and linking aims to link the core column mentions to the KB. We have three subtasks, steps. In the first step, candidate selection. So for any core column mention, we retrieve the top K candidates using Wikipedia search. So again, here, we're still using this table as example. Assume we have already known the leftmost column is the key column listing all the hospitals. So what we do is we retrieve the top K for each of the mention, and then we get a matrix here. And then we will use the top ranked candidates to vote by a majority vote to taking their type in the KB to vote the table based on Baptist hospital and the rest of things. And we find, okay, the type of this table is hospital. And we take this type as a soft constraint. So why is soft constraint? In literature, there are some methods using this type to exclude the candidates in this step. It resulted in a pretty low recall. That's why we put it in a later stage, just using it in a very light way. So after candidate selection, we got a bunch of candidates. What we do is we will classify these candidates by considering the lexical similarity and the semantic similarity. It's given any of the mentioned and their corresponding candidate. So we compare the string level similarity, such as edit distance, Giga similarity, and then we additionally compute the semantic similarity using a deep semantic model. And then we will do a binary classification. We predict if this candidate should be linked or not. And then we have kind of a matrix. But sometimes we got like multiple ones, which means we find probably is very confusing. We might need to link to like multiple entities, which is not correct. And what we do to fix this is by entity disambiguation. We utilize the table type now as a lightweight disambiguator, and we our filter will keep only the top rank candidate have the same type with the table. Now we only got the first one. For each row, we get at the most one candidate linked. So this is a basic idea how we deal with anti-linking. The second task is doing something similar, but in a different direction, column heading property matching. So now it aims to match table headings to KB properties or predicates. This step actually relies on the results of anti-linking. So in the candidate selection state, we take all the properties of linked entities in the KB as a candidate. For example, still by taking an example, the hospitals. Well, for the first hospital, we might get their properties in the KB like number of beds. And for the second hospital, we might get a revenue. Then we will put all this property together as a candidate, and then we will classify this candidate to any of the headings by consider the three groups of features. So the general idea is we only classify or do the schema matching based on the same type. So number to number, date to date, string to string, and other to other. And the three group features, naive features like showing the characteristic of the mention, such as if the column is a column or the length of the headings, level similarity is not surprising. So we only compare the headings against the predicates on the string level. It's because the top 5 most popular headings in one public type corpus are release date, elevation, population total, location, and industrial. Even top 10, we can find most of the headings, their corresponding predicates easily in for example, in Wikipedia. Then this is the idea why we decided to use level similarity. And the value similarity, it classifies values as time, numerical, and a string and other for any values in the cell and in the objective. Just imagine all the cells in the same column, and we take their values, compare against all the values or objectives for the linked entities we did in a linking step, and their predicate objectives. Just by time, and numerical by numerical. The one thing which is interesting is when we compare the number or time, we didn't do exact match. Why? Because the numbers might change slightly. For example, for the population of a town, let's say last year was 500 people, and this year they got 510. So this number might be changed slightly. We call it like temporal aspect. To avoid this, by exact match, we calculate their standard deviation to compare the time value, numerical values, and also for string values, we compare edit distance, for example. So this is the general idea, how we compare the value similarity. So now let's have a look where we are. After the first step and linking and column heading property matching, we have now map part of the dimensions and headings to KB, and we focus on the gray things, the unlinked things. We'll figure out why we failed to link this by the classification. No entity classification classify the unlinked mentions in relational table as in KB, out KB, or not entity. So here's a repetition. Here, I just simply list the three kind of solutions or aspect how we can resolve this solve this problem. Origin and characteristics. For example, we use if a mention appear in tables in which majority of mentions are linkable, because for a single mention, no matter like which table it come from, it might duplicatedly appear in multiple tables. Now we take their ending results or characteristics as kind of input or signal. This is origin characteristics. Silence assisted entity discovery, it utilizes the linked mentions as inference. So what does that mean? Let's have a look at this illustration. A, B, C, D, E in a table, they originally in the same table, but now A, B, we have already find their corresponding entry, like Wikipedia A and B. So what we do is we try to clarify C, D, E by utilize the correspondence above. So how? So it's actually in semantic-based entity discovery, we continue to use the idea. For example, we use a neural embeddings and topical space, such as, because now we have already know, okay, A and B, they are corresponding to Wikipedia A and B, right? And for C, we get C1, C2, CK, they are candidates. And then we'll compare their topic space, such as the categories in database, to see how they're consistent with each other. And also we use the lexicon space. So this is a general idea for our classification. Entity resolution is a very tiny task. It's trying to group the different aliens with the same type. Two subtasks, type resolution. It's trying to answer, does a mention appear in different tables refer to the same type? For example, DSP, it might refer to digital signal processing or company. But if it comes from different table, how we resolve this, right? So we use the histogram similarity, which is a type histogram. That is, if most of its neighbors refer to a company, then we assume DSP refer to a company. This is a type resolution. Surface form resolution is trying to answer, do similar mentions refer to the same entity? It's deal with aliens. For example, Cisco System Incorporated and Cisco might refer to the same company at some level. And what we do is we can mention to vector, mention similarity on string level and table similarity, and to see how their original table similar to each other by comparing headings, caption, link entity. For example, let's have a look at this illustration. For these two tables, what we do is consider trustees of Boston Uni and trustees of Boston. They align in two tables like the Google Patents table. By caption, of course, they're slightly different, but by headings, they're exactly the same. And for the entities, if we consider overlap, of course, there are not so many overlap, but if by type, all these like applicants are organizations, which is very similar. So what we need to do is we need to distinguish, although these two mentions is quite different, we have to distinguish, they should put it into different groups. So this is entity resolution. Now I will give you a very fast introduction about how we did the experiments. The data we use is WDC relational tables, which has 50.8 million tables, and we use Wikipedia and DPD as a node base. For linking and heading property matching, we consistently use T2K, which is a public text collection golden standard. You can keep using it. Here's one suggestion. If you are interested in linking in web tables and you want to use T2K, so you might need to do some extra work, because the tables here on average have 26 rows, which is much larger than Euro. Because, for example, Wikipedia, the average number of rows is like 6, 7, I guess. And here it's like, larger tables is easier to do than linking. That's why if you want to do a fair job in future, and you might need to extend T2K. Yeah, and also comparing to Wikitable or T2K, Wikipedia and linking for Wikipedia tables is much easier compared to web tables. For the rest two tasks, we built our own test collection using crowdsourcing. Now, have a look at each step. So we evaluate the result based on the two test collections. And for experiments, we utilize a public Wikipedia surface form to filter tables. And the table should contain at least one surface form from this collection. And in the end, we got 16.2 million tables that is useful. Because for this public Wikipedia surface form, if you have interest, you can CC me. I can send this for filtering. And in the next step, we perform unlinking using the model trained based on test selections for tables that have a majority voted table type. And we find like 3 million tables that are linkable. So here are the results. I only want to highlight one thing here, Wikipedia search. Let's have a look at the results for T2D. It's very surprising that Wikipedia search is a very unsupervised method. What we did is like just do a very simple filtering. And so we got very high precision for T2D. And we build based on that, and we re-rank, and we distinguish the entities, and we have very good results here. But I want to highlight here, so we actually built based on Wikipedia search. So we won't overclaim on contribution here, because for unlinking, I think there are still a lot of potentials for this task, especially for tables. I just want to share some takeaway points, which is important for people who are working with unlinking in tables. So do consider Wikipedia search for the candidate selection step. Just see how that works for that. And also both lexical and semantic similarities contribute, which is not surprising. And also column values. So we didn't use column values for unlinking. Yeah, column values, of course, can bring some signal for unlinking, but in this case, for unlinking, maybe it's like too much noise here for this task. And table type works better in later stage. So we didn't exclude the candidate in the first step, and it's a bridge towards null entity discovery. For schemation task, so we rely on the results of unlinking. So we use the 3 million linkable table for unlinking, and then we execute this schemation for 3 million tables. We find about 181,000 tables that have at least 2 heading property correspondency, Y2, because we have a key column in the table, right? That is very easy to find correspondency. So we have to ensure we can find correspondency for the rest of the properties. And compared to T2K in the result table, the main difference here, we didn't consider iterative state, and we additionally consider level similarity. Then it's actually our contribution, like takeaway points. Level similarity is important. Yeah, by like intuitive, it is by, in the baseline, they didn't consider it to use the level similarity. And in contrast with unlinking, the values for schemation is important. And we plan to discover some new schema at the beginning, but it's left over now. Now, the last part of null entity classification, we built our own test collection by assembling 20,000 unlinked mentions. Here, I just share some very interesting sorts. We have 3 million linkable tables, right? And after unlinking, we find 3.4 million identical unlinked mentions, and we sample 20, and we find about 39% of mentions are in KB entities, 55 are out of KB entities, which are new entities, and 5% are not entities. We filter these by like manual state of the not entities. The result table is not surprising when we compare different aspects. One thing I want to mention is the first bias baseline, slope, and R-square, they use the time-based method. However, time-based method does not compare here for tables, because the mention in tables it's with bias, and the 3 aspects complement each other, and there's a trade-off between linking and null entity discovery. That's mean. So of course we want a good result from unlinking. If we can do 100%, now the null entity discovery will be much easier. However, yeah, we are limited by the recall or precision. So we have the good thing for us is we have null entity discovery for making up. Now here's a summary. So we plan to discover new entities from web tables for knowledge-based population, and we do it step by step because given the raw tables at the beginning, we don't know where we can end up with. That's why we kind of want to have a good control of each step. For unlinking, I encourage to use Wikipedia search for candidate selection. For column heading properties mentioned, so do consider lab similarity, although it's very intuitive. And now entities classification have to verify the original idea that is, there are many null entities in the table undiscovered. And we have a very good solution for entity resolution. So for anyone that have interest in this work, you can find the data set from this link. So we not only share the links, but also share the 3 million tables with all the entity correspondency and schema results. Because if you use Wikipedia tables, that's easier because they already have the linking results. But for web tables, so we're the first to share such kind of resources if you want to work with tables with linking results. For the future, of course, linking is never ends. And also we plan to discover new schemas at the beginning. Now it's left for the future. Okay, I think this is everything I want to share here. Just to remind you one thing. So please have a look at this website if you are recently on the job market, because we are currently hiring. I'm not sure if we can have a proper QA station. You can ask questions directly or leave a message to me. I'm not sure. So that's it. Thanks very much.